My name is Jacob Austin from Columbia University, and I'm here to present work done with Professor Hod Lipson at the Columbia Creative Machines Lab. Before I start, I want to wish everyone watching this from home all the best. I'm here to talk about new software for soft robotics, topology optimization, and robotic evolution. Soft robotics is still a very new field, and very different from classical robotics when it comes to simulation techniques. Soft robots no longer have just a few degrees of freedom, they use deformable materials, and they no longer even necessarily have a fixed topology. This means existing simulation software tends to be at best hard to use, and at worst tends to lack support for the kinds of parallelism or low overhead topology optimization necessary for large, high fidelity simulations or soft robotic evolution. On the bright side, soft robotics and soft robotic evolution can benefit enormously from hardware support for parallel kinematics and from data structures that support low-cost modification of existing robots. Existing libraries, even those that value parallelism like MuJoCo, use CPU-based kinematics algorithms based on linear or quadratic programming solvers to accurately handle contact physics. These are accurate, but they don't handle large systems of interacting particles well, and critically, they cannot take advantage of GPU parallelism for concurrent simulations. Topology optimization, robotic co-design, and soft robotic evolution have become increasingly important in the robotics community. So apart from some of the obvious requirements, like high performance and physical fidelity, simulation software for soft robotics also needs to be able to modify the topology of the robot with low overhead. Existing software tends to either require fixed topology during a simulation, or else has prohibitively high computational costs associated with modifying components of a simulation. Existing libraries also do not support asynchronous communication between the CPU and the GPU to allow the CPU to perform optimization algorithms while the GPU simulation proceeds. In our paper, we present Titan, a new open-source C++ simulation library for soft robotics. Titan is a general-purpose framework for defining and simulating soft robots using a spring mass approximation. It's also an asynchronous library for simultaneously optimizing and simulating soft robots and multi-agent systems. It also functions as a library for parallel reinforcement learning simulations, where physics is scaled horizontally across a GPU. Titan is able to achieve up to 100 times performance of a CPU-based algorithm, up to 3 million masses on a single GPU in near real time. This is close to 300 million spring updates per second. Titan also achieves constant time insertion, deletion, and modification of components in the simulation, all performed asynchronously from the CPU. Contact forces, constraints, and asynchronous CPU-GPU control are all supported. The robot you can see in the background is a soft locomotive worm which uses friction and periodic actuation to achieve motion. This worm has around 5,000 internal springs and close to 1,000 masses. And here are 100 of these worms being simulated in parallel in real time. All of these videos are real-time captures from our OpenGL interface. Our library supports simulations of some of the largest soft robots and soft robotic systems of any existing library, and the performance scales linearly across new generations of GPUs. As a software library, our goal for Titan was primarily to require fewer lines of code and less custom logic for soft robotics projects, while maintaining high performance. We want to enable topology optimization of robotic structures at high speeds, asynchronously from the GPU, and achieve high performance in any situation, including contact physics, friction, constraints, and extremely large or dense lattices. We also prioritized extreme scale. This means that masses and springs need to have low memory overhead to allow scaling of up to 3 million masses on a Titan X GPU, and further scaling to new generations of graphics cards. We also want Titan to be easy to install, easy to learn, and easy to incorporate into new projects. For this reason, we also include a Python interface. Before we get into the implementation and design details for Titan, I want to walk through an example of our code. First, you can define a robot in a variety of ways, either using predefined primitives like masses, springs, or lattices, or by loading robots from files in common formats. Then, you can set simulation parameters, and finally run the simulation, which critically runs asynchronously from the CPU and allows you to continue optimizing until you want to synchronize. The first core observation about Titan's implementation is that simple kinematic solvers work surprisingly well for soft robotic simulations. This runs counter to prevailing sentiments that rely on more sophisticated methods that are less parallelizable. But we have found that a simple Euler integration method, or more sophisticated schemes like Verlet integration or RK4, achieve high physical fidelity when time steps are kept low, but remain far faster than more serial methods. The core logic of Titan simply applies modified Hooke's law forces in parallel to all masses, and then updates their positions and velocities in parallel using only a minimal atomic or reduction-based synchronization for spring force updates. This parallel integration scheme is much faster than other methods and achieves accuracies that match analytic results and conserve energy and momentum, even in systems with friction and other contact forces. For example, for a simple bouncing cube benchmark with 8,000 masses and over 93,000 springs, we note conservation of energy to within numerical precision over long timescales. Besides being fast and accurate, our overriding design goal for Titan was to support efficient modification and optimization of the simulation in real time. Here you can see a cantilevered beam being optimized for low weight and maximum strength in real time, with optimization performed on the CPU while the simulation continues on the GPU. This is especially useful when optimizing structures for 3D printing. To make this possible, we designed a set of data structures that allow constant time insertion and amortized constant time deletion, as well as constant time access. We store an array of pointers to both masses and springs on the CPU and GPU, which are reference counted, and deletion simply requires marking masses as invalid and decrementing the reference count. Insertion is done using a C++ standard library style vector. Topology optimization and co-design is also made possible by an asynchronous communication model between the CPU and the GPU. A background CPU thread constantly launches CUDA kernels to perform simulations and track simulation requests from the CPU. For the most part, the CPU and GPU run separately with no communication overhead, only stopping to perform limited data transfer and synchronization. We benchmarked Titan against a CPU implementation, where it achieves up to 100 times performance increase on a Titan X GPU. We can fit up to 3 million springs onto a single GPU, and achieve throughput rates up to 300 million spring updates per second. This is difficult to directly compare against other libraries, but for a simple bouncing cube benchmark, it is between 2 and 8 times faster than NVIDIA Flex, and comparable with Taichi, usually around 85% performance, despite overhead incurred by the asynchronous runtime and data structures. It surpasses both on topology optimization benchmarks. We also compared Titan to both analytic results for simple systems and real soft robotic components. Here you can see a soft pneumatic cell compared with the simulation in Titan. There is also significant interest in multi-agent robotics, where independent agents interact to achieve some kind of collective task. Here, independent agents achieve collective motion using contact forces and synchronized actuation, all captured in real time. Multiple interacting agents scale horizontally across a GPU. Briefly, it's also worth mentioning that Titan can be used for reinforcement learning, where multiple simulations can be scaled horizontally across a GPU for algorithms like asynchronous actor critic. Titan also makes building and designing new robots easy. Robots can either be imported from common file formats like STL files, where we automatically build lattice approximations, or from sets of common primitives like beams, lattices, and masses and springs. Finally, Titan is fully open source with an Apache license, and available on GitHub at jacobaustin123/Titan. I'd like to briefly thank the Columbia Creative Machines Lab for their support, and acknowledge DARPA and a trades grant for supporting this project. I'd also like to thank ICRA and our reviewers for making the paper much better. Thank you.